Absolutely.
It's
Yeah.
it's recording now,
So
right?
yeah,
Okay, cool.
yes.
Good.
Uh, okay. So I'm from Emory University, and I'm a computer science PhD candidate at Emory University, soon going to defend in 2 weeks. And yeah, I saw some of you are here at Boston as well. So I'm gonna start my postdoc at Boston College with in the computer science department. So hopefully I maybe meet some of you in person. Uh, yeah, so my research interest are spatiotemporal data mining, applied machine learning. Specifically, I deal with transfer learning and domain adaptation models. And like my preferred use case that I apply these techniques is for environmental science, especially air pollution or PM2.5 modeling. Uh, so my dissertation is transfer and integration of knowledge for irregular spatiotemporal data. And the advisors that I work with are Andrea Zufle and Avni Veldani from computer science, and Dr. Yang Liu, he is from School of Public Health. He's like a close collaborator or an advisor adjacent. Yeah, so that's about me. If you guys have any questions for that, I'm open, or we can just move to the presentation if that works for you, right? Yeah, okay. So today I'm here to discuss my paper, Spatial Transfer Learning for Estimating PM2.5 in Data Poor Regions. This was published in the ECML PKDD conference. Uh, and let's dive right into it. Uh, Okay, so I'll go over the basics first, like what transfer learning is. So traditional machine learning is where you have one data set, you put it into a machine learning model, and you the output are the predictions that you get. Transfer learning, it's basically where you the knowledge is learned from performing one task, and then this knowledge is transferred to another similar task. So uh, the knowledge that or the data, or sorry, the task you're learning from is actually called source domain because it has a lot of data or it is data abundant. And the task you're applying to, or like where you're applying knowledge to, that's called target domain. And it's usually data deficient because it has less number of samples. And yeah, so basically transfer learning is just translating knowledge from data abundant task to data deficient task. Okay, transfer learning has many aliases. So one of the famous aliases is domain adaptation. So the traditional domain adaptation, it was defined because usually training and the test data set, they don't usually have the same distribution. In a traditional machine learning case, the training data set and the test data set are like mutually exclusive. So you don't try to take instances from the training data set. So in the, so the machine learning models required use case where if these two distributions are different, can you adapt distribution in training to the test distribution. And this is what domain adaptation was initially. And this domain adaptation framework can also be applied to transfer learning, where if you have like a source domain data set, can you reweigh the source samples in such a way that they are similar to your target domain data, which you have and which are very less in size. So domain adaptation is another alias for transfer learning. And domain adaptation seeps into a kind of transfer learning which is called instance transfer learning. So instance transfer learning is basically like I said, you use the source domain instances directly. So uh, classical transfer learning, the way it works is that you take the source domain, you create a model, machine learning model. Then you use this machine learning model, you fine tune its parameters on another domain, which is the target domain, and then you do the predictions. But instance transfer learning is different from it. Instance transfer learning basically just takes your instances or samples from both the domains and it combines them. And the way it combines them is it reweighs the source domain and it so that they are similar to the target domain, and then it combines two domains. So this reweighing is actually very important, and this kind of reweighing we also see in domain adaptation. So you can say that instance transfer learning and domain adaptation are very similar ideologies. All right, so what the PM 2.5 problem is, uh, as we all know, particulate matter 2.5 are aerosols which are less than 2.5 micrometers small. They pose significant public health concern that they're small enough to enter bloodstreams and cause heart diseases, as well as they can enter lungs and cause pulmonary diseases. They are caused due to vehicles, wildfire, and industrial processes. The need for transfer learning. Okay, so like data which is often collected. So data can be collected in two ways. One is that you collect it using remote sensing methodologies that is using satellite observations. This data is often inaccurate and compromised due to factors such as cloudy weather and high surface reflectance. Another way is that you can install ground sensors, which are very highly accurate, but their installation, scaling, and maintenance is costly, especially for developing regions or developing countries. And this is where transfer learning comes for rescue. So since transfer learning is based on the ideology that you can transfer knowledge learned from one task to another task, you can do this in the case of PM 2.5 prediction as well. So basically, you transfer knowledge learned from one region, which is the data rich region, to a region with less data or the data poor region. Okay, so we defined what spatial transfer learning is. To understand what spatial transfer learning is, we focus on what transfer learning for PM 2.5 has been previously. So prior PM 2.5 studies, they focus on forecasting models. Forecasting models are basically models which train on historical data for locations, and they predict future values for the same locations. So these have certain limitations. One, if there are missing temporal points, which is often the case, they are not very well suited for this scenario. Second, if you're trying to predict on unknown locations, again, they're not then suited for it. And as well as they're not suitable for sparse train and test locations with low spatial autocorrelation. So this is where spatial transfer learning framework comes into place. Spatial transfer learning is basically we use instance transfer learning models, and we try to capture the spatial characteristics of the data using these instance transfer learning models. An example of this is where we're trying to we have these train sensors which are in green, and we're trying to predict on the red test sensors, which are a lot as compared to the training sensors. uh, okay, so what is our proposed solution? uh, we have focused on instant transfer learning. So instant transfer learning models, we know that they are unaffected by missing temporal data, like which is not the case for I'd say the forecasting models. Also, these models combine source and target domain data, which is actually useful because since there can be missing values, this kind of combination can help uh, fill up the data set. So our proposed solution is, how about we add a new feature that accounts for spatial dependencies and semantic dependencies. So what do I mean by spatial dependencies and semantic dependencies? So given the data set and given that this is like a data set which has ground sensors, basically location-based data set. So we do note that the nearby locations, they can have similar PM2.5 levels, which is like a popular geographic law as well, that nearby locations behave in a very similar manner. So these dependencies can exist, that nearby locations may have similar PM2.5 levels, as well as semantic dependencies, which means that if two locations, they have same meteorological and topographical conditions, they will also have similar PM2.5 levels. So if these dependencies are existing in the data set, and traditional machine learning models and transfer learning models are not able to exploit it, uh, we believe that a model should be created that is able to do this. And this is what we propose as a solution, to exploit the dependencies, to include it in our solution. So our model basically it learns the spatial and semantic dependencies. It creates a new feature, and this feature is then added to the original data set. So if we have a set of features or predictors, which are meteorological features, topographical features, and temporal features, we learn dependencies existing in this data set. We create a new feature, and we add this feature to the original data set. So the contributions of this paper is that we present a new feature, LDF, which I expand on to what LDF stands for, latent dependency factor, which represents spatial and semantic dependencies. We also introduce a novel two-stage autoencoder model to generate the LDF. We explore and design solution to the problem of spatial transfer learning, and we deploy our model on real-world data. Okay. Before I move forward, if there are any questions, just feel free to interrupt or just let me know. Yeah. Okay. So the framework of our methodology is that it consists of three stages. Basically, the first stage, we create the neighborhood cloud or neighborhood cloud generation. The second stage consists of generating the latent dependency factor. And the third stage involves transfer learning followed by multivariate regression. Okay, I will go over each stage one by one. So the neighborhood cloud generation stage. So basically, in the first stage, we compute similarity between sensors, both the target and source location, to find a neighborhood cluster. Basically, we're trying to, for each location, we create a neighborhood cloud structure which has 12 neighbors, and it is composed of both the source and target samples. For similarity or for creating the cloud, we use the Euclidean distance or the Euclidean similarity. We combine in this way the most similar M stations, M being 12 here, and then the data for each station is tagged to form a larger data set. And this data set is called neighborhood cloud data set. And how we arrive at 12 as a number, it is something that I discuss later on. Then we generate the latent dependency factor. So this consists of two stages. So we created a two-stage autoencoder model. The first stage is the basic encoder-decoder model. So an encoder-decoder model, it has an encoder which encodes the data that you feed it into a latent value, and then decoder and encoder are connected through backpropagation, and they correct the value to, so that it's very close to the validation set that you have. So uh, the encoder and decoder each have three 1D CNN layers. Uh, and the information from the three CNN layers, like I said, is summed up using uh, an FNN layer, which outputs the LDF value. In the second stage, which is the encoder estimator stage, we add an estimator layer. This is basically to increase the attention on PM2.5 values of an objective location. The estimator has a single FNN layer, like you see here. So this is the encoder decoder model. This is the latent value. The latent value is also fed to an estimator layer. And then the estimator layer is connected or uh, is connected to the PM2.5 value of the objective location. So this location, since it's blank here or represented as black, this color, so this is basically translated to this PM2.5 value. So the estimator value is trying to correct or trying to learn the closest PM2.5 value of the objective location here. So finally, the latent value that you get, it's very closely aligned to the PM2.5 value of the objective location. And in this way, you do this for every location and you fill the final LDF feature with all these values. We also created one more feature, which is LDFA. So not just PM2.5 value, but we also use the aerosol optical depth uh, value in the encoder estimator stage. So basically both PM2.5 and aerosol optical depth values. And then we created the LDF value using it.
Could I ask a quick question?
Yes.
If you go back one slide, so the autoencoder, the inputs and the outputs of the encoder decoder is the same thing where you kind of compress and reconstruct that original image with the latent space being that you want it to. Do you just save out the latent space as the LDF, or is the LDF
Yeah.
something that you okay, so that's your like
Decoder.
mhm.
So
Go
yeah,
ahead.
so the decoder has no output. Basically, using backpropagation, we're just feeding the encoder, and then encoder is generating the latent value. Since we are not gonna like, we do not care what decoder value is. What we are focused on is this latent value, and that will become our LDF value.
So the encoder, you just take the compressed representation of that latent space and save it out. You don't apply constraints, or is it just like lossy compression of that?
What do you mean? Can you elaborate? Like, what kind of constraints?
Like, for example, you want it to mimic some kind of PCA or nonlinear compression, or or you want it to look like something that the LDF one factor has to be related to meteorology, one factor has to be related to space, etc. Or it's just like you compress it like in a PCA or a dimensionality reduction
Yeah,
technique.
it's more similar to, I would say, dimensionality reduction. But yeah, that was something that we also wanted to explore. Like, what if LDF has like this different components? It's just not one LDF, like it's maybe one meteorological LDF and one topographical LDF. But yeah, in terms of what kind of reduction we're doing, you can say that it's more dimensionality reduction per se. But we tried with PCA as well. We tried to do this with PCA where we and I don't have the experimental results to show it, but when we were generating this, we tried to do it with PCA as well, and the
Okay.
results were not like good with PCA. So we then just went ahead with this kind of model. But
Okay,
yeah,
so I guess like number one here is kind of the characteristics of the data, but two is kind of the machine learning, you're predicting PM 2.5 aspect of it. Is that kind
y-
of what it is like?
like the reason this works versus PCA, or like
Oh, just like the one versus two, like two, it's the machine learning prediction of PM 2.5. One is the construction of this latent variable. Is that basically what it is?
I'm sorry, I'm not, is are you talking about
Yeah,
this
those
one
one
and
and
two,
yeah,
or
sorry, those one and twos.
so
Where mhm.
this is just the stage. One stage is, yeah, this is the encoder decoder stage, and two is the encoder estimator stage.
Okay.
Uh,
Yeah, I can follow up after. Sorry to interrupt that. Thank you.
no, no worries. Yeah. Okay, and then yeah, coming to the third stage, which is the transfer and regression. So once we have the LDF data set, the next stage is to do transfer learning, where we basically, this is our LDF data set, this is the source data set, and this is the target data set, and both of the LDF features are attached here. Uh, Sorry, this is yeah. Uh, yeah, so this kind of instance transfer learning happens over here. And the source data set is basically reweighed so that it's similar to the target data set. And for this kind of reweighing, we use different kinds of transfer learning models, which I elaborate later. Once this combined data set is formed, this being the target and the source, we push it into a regression model and we generate the estimation. So yeah, the steps can be summarized as basically applying instance transfer learning on a combined LDF dataset to generate source sample weights, and then applying regression on the weighted source plus target samples to predict the PM2.5 values. Okay, so for a fairer comparison, we used two machine learning models, and for some reason, I've just described one machine learning model, but we use random forest regression and gradient boosting regression. So to elaborate on gradient boosting regression, it's an ensemble model of decision trees to minimize the pseudo residuals, and then it's applied on the so this is applied only on the target data set, and no source samples were used here. And the transfer learning models we used were, there were four kinds of transfer learning models. So the three of them were instance transfer learning models, basically applying domain adaptation. And the fourth one was a parameter transfer learning model. So parameter transfer learning model is like a classical transfer learning model where you translate the neural model and then you fine tune it on the target domain. So for the instant transfer learning model, we use the nearest neighbor weighing. So in nearest neighbor weighing, the source samples are reweighed by creating a Voronoi tessellation for to calculate the how many target samples are lying in that tessellation, and then reweighing is done based on it. And then there was Kullback-Leibler importance estimation procedure. Basically, it reweighs the source sample so that it can minimize the KL divergence between the source and the target sample. And the kernel mean matching, instant transfer learning, it works in a very similar way. What it's trying to minimize is to minimize the mean of source and target sample in the reproducible kernel Hilbert space. So, okay, sorry, this is the next slide. Yes, okay. All right. So what kind of target data sets did we use? So one was the California, Nevada region. It had 128 PM2.5 sensors. The data set shape was 200, almost 250,000 rows with 27 features. These features spanned over like meteorological, topographical, and geographical predictors, and it was from the year 2011. We also had around 19.5 million satellite samples, but these were unlabeled. So this yellow region over here, it was all the satellite data set. Uh, and then we also had Lima, Peru dataset. There were only 10 PM2.5 sensors in this region. The dataset shape was around 2,500 rows with 21 features. These features were similar meteorological, topographical, and geographical features, and they were from year 2016. And uh, so the common features that is stated here, it basically represents how many common features it had to the source domain dataset. And since the source domain dataset was also United States, so the number of common features between Lima and United States that we could find were 14. Uh, so the satellite samples that we had were around 6,000, and they were also unlabeled. Um, So the source data set that we used was the Eastern United US data set. It had, let me rephrase. So we had we used two kinds of source data set. One was the Eastern United States and the other one was Northeastern United States. So this green region is, sorry, the entire of this region is the Eastern United States, and just this yellow region is the Northeastern United States. So Eastern United States had 607 PM2.5 sensors. Northeastern had 147 PM2.5 sensors. The data set shape was accordingly. And it was again from year 2011. Basically, we had entire United States data set. We carved out California, Nevada region out of it re- and used Eastern and Northeastern United States as the source data as the source data set. Uh, yeah, and okay, coming to the optimal K. So since I just defined the LDM methodology, which consisted of creating the neighborhood cloud. And as I stated, the number of neighbors in the neighborhood cloud were 12. Uh, so this was chosen based on trying the NNW LDF model. And the reason we tried only this kind of transfer model, which is the NNW model, is because as you will see, it had the best performance overall. So uh, we chose like 4, 8, 12, and 16 neighbors. And in our analysis, K equal to 4 neighbors showed the worst performance, while 12 provides the optimal balance between computation and generalizability. Basically, computation with 16 was like it was taking a lot of time. And at the 12 and 16 performance were almost equal. So we went ahead with 12 neighbors. Uh, So experimental setup. So for the California, Nevada, the sensors were grouped into sets of 5, 7, 9, and 11 for cross validation, and we reported the R square and RMSE value. Average across 20 CVs. And we matched the daily active sensors. So basically, while creating the neighborhood cloud, since so to avoid repetition, because most of the sensors were active each day. So since we are creating neighborhood cloud for 12 similar locations and to avoid repetition, what we did is we took just the day values and we created neighborhood cloud for each day for each sensor. So coming on to the results. So for the machine learning models, like I said, and this is so I think I've missed to mention this. So these results first depict how transfer learning works when we use California, Nevada as the target region and the Eastern United States as the source region. So first we did machine learning modeling, and in this we only took the California, Nevada as the target region. We did not use the source region. We see that as the sensor number of sensors increase, the R2 and the R2 score improves, but the RMS score and the RMSE score decreases as well. And we see that gradient boosting regression had the best performance among the two machine learning models. Then we applied transfer learning with the 4 transfer learning models that we have. And we see that nearest neighbor weighing had the best performance among all transfer learning and when compared to the machine learning models as well. And then, okay, so to do a very, to just see, okay, so to just see which models were performing best, since NNW was performing the best and GBR was performing the best in ML, we just took those two models. And then we used NNW LDF, which means NNW model with the LDF feature, and NNW LDFA, which is the NNW LDF NNW model with the LDF-A feature. So when we use only the Eastern United States as the source data set, we see that NNW LDF has the best performance among all these top competing baselines. And when we use Northeastern United States, we see that it kind of jumps between NNW-LDF and NNW-LDF-A as having the best and the second best performance. So basically,
Actually,
we can say
uh,
that, yes.
sorry to interrupt. What's the target region for these two tables?
Yeah, so the target region is the California, Nevada region. The Lima region
Okay,
was not used here. Yeah,
okay.
I
Thank you.
like I said, I failed to mention that previously, but the target region here is the California Nevada region. Yeah. Okay. Also, like just to touch base with the broader results, when we compared NNW, LDF, and LDFA with the remaining transfer learning models, we see that NNW LDF is the clear winner when Eastern United States is used as the source data set. And similarly, when Northeastern United States is used as the source data set, NNW, LDF, and LDFA is clearly performing better than remaining transfer learning models. So we also did an ablation study. So basically, in ablation study, we compare the gradient boosting regression and transfer models using the LDF imputed data so as to validate its performance. We observed that addition of the LDF feature improves the performance of gradient boosting regression. So in this model, we see that when source Eastern US is used as a source, gradient boosting regression has a jump in the performance. Let me just put the graph. Okay. All right. This. Um, all right. So that's my bad that I didn't use the markers to represent which one was GBR and which one was NNWLDF. But as far as I can tell, I think GBR was the brown one and the yellow one was the NNWLDF, if I'm not wrong. And GBR had a very good jump in the performance when LDF feature was attached to it. However, it was still the second best performing model. NNW-LDF outperformed GBR still, indicating that this kind of methodology is best suited for transfer learning models. But we can also see that adding an LDF feature, it also improves the performance even for the machine learning models. Uh, yeah. So for the qualitative results, so we created the qualitative maps where we saw that NNW. So just to define the three regions which we were focusing on, so this is the California Nevada region. We were focusing on the Central Valley, the LA Basin, and the Imperial Valley. And this is the ground truth. So the way this ground truth is generated, since we don't have the satellite uh, data labels, is that we trained on 128 ground sensors, which were in the California, Nevada region, and then we predicted on the remaining satellite observations. And this is an assumed ground truth. It's not the true ground truth, but we were trying to see if our generated or estimated PM2.5 values are closer to this. And so as we see in this, NNW LDF has the most accurate PM2.5 estimation, especially in the Central Valley and the LA Basin. However, it slightly overestimates, I believe, in the Imperial Valley. NNW LDFA has the second best performance. It estimates However, its estimates in the Central Valley are a little patchy. And then if you see the NNW map, the NNW model shows obscure and patchy patterns. It underestimates in the Central Valley and it significantly overestimates in the Imperial Valley. Okay, so coming to the Lima dataset, since we didn't have a lot of sensors in the Lima region, so what we did is we only did the qualitative analysis in the Lima region, and this qualitative analysis was validated by the environmental scientists that we were collaborating with. So we focused on three regions mainly: the coastal region, the inland, and these Andes mountain region. So this is the NNW prediction, the NNW LDF and NNW LDFA. So we see that all models show lower PM2.5 levels near the coast and higher levels inland, which is great. However, we see that NNW LDF has a clear inland concentration, and near the Andes mountain, which the environmental scientists we were collaborating with, they stated that it should have lower PM2.5 levels. The NNW LDF model was able to capture this the most clearly, and then followed the NNW LDF and sorry, the NNW LDF-A model follows this. It's able to capture these concentration gradients much more clearly than the NNW model. As you can see, the NNW model is not very well defined. The estimations of it is not very well defined. So we also did, like, given the less number of sensors that we did a 60-40 train test split on the sensors to show that NNW LDF, which shows that NNW LDF clearly outperforms NNW with better R2 and RMSE values. The NNW LDF had a value of 0.55 as R square and 9.09 as RMSE, whereas NNW without the LDF feature had a R square of 0.47 and RMSE of 9.85. We also did some exploratory analysis. So we do realize that LDF, since it's basically trying to capture the essence of all the features in both the source and the target domain, it should basically be most correlated to the dependent feature, which is the TPM2.5 feature. And we did a correlation test, and we showed the top 5 highest correlation features, and we see that LDF feature surpasses other feature by a lot of margin. That is, it is highly correlated to the PM2.5 feature. And I already stated that the deployment in Lima also proved that LDF feature has a better prediction than the NNW feature. So coming to the future directions of this research, where do we see this going? So we want to incorporate data sets basically which lack spatial and semantic dependencies to broaden the scope of PM2.5 estimation. So basically what I mean by this is, like, usually the PM2.5 the PM2.5 data sets available through open source or which are openly available, they are not that complex. They usually have very few features, and they might lack a lot of spatial and semantic dependencies, which is usually present in these dense and high dimensional data sets. So we want to try how this kind of methodology applies to those data sets as well. Is it useful for such data sets? The second is that since this feature only captures the spatial trends, and we basically ignore the temporal trends due to missing time series values, can we also incorporate temporal trends in some way? Can this CNN model be maybe converted into more of like a CNN LSTM model, which can basically also capture the temporal patterns in the data set? we believe maybe this will enhance the LDF feature. And the third is like how if we can expand it to other domains like maybe wildfire estimation or weather forecasting, which consist of similar spatiotemporal patterns. And yeah, basically, so in this research, we did spatial transfer learning, which is basically a use case for transfer learning between highly sparse and distant source and target regions. We created a new feature called latent dependency factor. We also designed a novel two-stage autoencoder model to generate the latent dependency factor. Our quantitative results show that if we impute LDF feature, it shows a 19.34% improvement over classical transfer learning. And our qualitative results show that LDF feature was successful in capturing varying concentration gradients accurately. And yeah, thank you. These were my collaborators over the paper. And this is the GitHub repo that you can check out.
Thanks, Shrey. Very good presentation. Nice talk. And now we have some time for questions. I have one question. So you use when you create the clusters to generate the LDF, you consider both the spatial and the semantic dependencies. So when you do that, does all these variables contribute the same to calculate the distance between the target site and the source site, or because maybe some variables is more important than others? And a following question for that is that, like in different seasons or even different day, that due to the change of the meteorological conditions, that the clusters should be changed. Did you generate the cluster for each day, or is like keep the same for the whole time series?
Yeah, that's a good question, actually. So regarding the importance of features while creating the